All right, recording is re-rolling. We've been outside and back, and oh, whoops, sorry. There's a solution. All right, so the general solution. Okay. So you guys launched a few launches. You guys were keeping track of. Okay, you guys know the massive ball. I gave that to you. Okay. You got a few trials. Now it was all the same ledge height. All right, since I just started the recording, what did you guys get again for your ledge height? About 5 meters. About okay. Okay, and okay, so that was definitely consistent. Okay. Now the horizontal displacement, maybe it varied a little bit plus or minus, but it's probably like some average value you could get, right? Average value. Okay. Okay. And from that, you should be able to apply some kinematic equations and come up with a conclusion of what's the blast speed. Right? So from scratch, right, here's kinematic equations you get to work with. Right? Now, anything that's involves acceleration could be any three of these. Okay? Maybe you want to know what is the ledge height and maybe what's the fall time, which would make you hone in on the first one, right? You might call, now X could be some general displacement, but in this context, maybe it's the ledge height, right? I could call it H for the X is H for height, right? Be like this right here, right? Now guys, if you aimed the cannon horizontal, which you did, what is the initial velocity in the vertical direction? You aimed it horizontal. How fast is it moving up or down when it's leaving the cannon barrel? 0 meters per second. Now it's moving really fast to the side, but it's not moving up or down at all. Remember, these equations, you have to take one dimension or the other. It's either all horizontal or all vertical. And if it's all vertical, this V naught is really V naught Y. So this would go to 0, wouldn't it? So we got H equals, this term just goes away, and H equals 1/2 GT squared. Oh, hey, that's the college equation, isn't it? Right? Height of fall is 1/2 GT squared. Right? Right. What if you blasted a ball horizontally and you dropped the ball at the same time? Would those two balls hit the ground at the same time? They sure would. Right. So we got the same equation set up for those. Okay. And that's this right here. H equals 1/2 GT squared. Okay. Now you can use this to solve for the time of fall. In fact, if you guys had a height of 5 meters and a gravity field 10 meters per second squared, what's 2 times 5 divided by 10? That'd be 1, right? Right. And then if you take the square root of that, you get a time of fall of about 1 second. Now, if you got a height anything different than 5 meters, maybe you got like 4.4 meters or something. I've seen that before, right? I bet the time would be a little bit less than a second. Or if you got like 5.2 meters, maybe it's a little bit more than a second, right? This should be in the ballpark of about a second, right? Right. So now you can calculate the time of fall. Right? All right, now let's switch over and look at horizontal. Right? So pick up and look at horizontal. Now, horizontally, there's only one equation that could ever really apply, right? Because acceleration is 0, right? There's no horizontal acceleration. If that's true, it just simplifies to that right there. That's it. That's the entire thing. X equals vt. Boom. Right? In this case, this represents the horizontal velocity. V represents the horizontal velocity, which is the blast velocity because you aimed the cannon horizontally, right? Now, you just found the time of fall, right? Pretty close to a second, about a second. And you know how far across it went because you measured that with either the meter stick or the trundle wheel. So you know how far it went. You know the time of fall based on the vertical motion. Divide those two and get how fast it's going across, which is the blast speed. And then there's the general solution in terms of variables. Right. Good. Now, of course, you guys would just come up with a number. I'm just looking for a number, right, of meters per second. Okay. So your conclusion is going to be the blast speed must be so many meters per second. Okay. So, for example, let's do an example. Suppose the height was 5 meters exactly, which makes the time of fall 1 second. Okay, so got that. Okay. And suppose it went out. What's one of the horizontal displacements you guys got? Finn, what did you get for a horizontal displacement?
15.
15 meters? All right. So if it went 50 meters across during a fall time of 1 second, that would make the blast speed equal to 50 meters per second. That could be the answer, right? Or everyone had a little bit different equipment, so maybe yours was a slightly different number. Okay. Okay. Any question on how to finish that off? Okay. So does everybody have a blast speed in meters per second? Right? And you guys do have units attached to it, right? Like nobody just wrote V equals 9. So you need like 9 meters per second. You know what units we're talking about, right? Okay. Right, that's good. All right. So once you have that, You got all the stuff. You guys got the table. You got your name on it. You got the calculations. You got the solution. Just turn that into the grade tray sometime before you walk out of class today, and I will get points in the grade book for you. Right, you guys good on that front? You guys good there? Any questions? All right, because we do have some class time left, and what I want to do at the rest of the class time is help you guys out a bit more on these puzzles. These puzzles right here. All right, let's do number 11 through 14. This scenario on the top right. Scenario on the top right. Zoom in on here. Okay. You got cannonballs fired at a speed of so many meters per second at an angle of so many degrees above the horizontal on a flat plane. Ooh, on a flat plane. Okay. Now all of us have different numbers, but we all have that same type scenario. Okay. Okay. Because whenever you see a cannon ramp up to some angle on a flat plane, I can tell you what the first step always is. The first step is always break the blast velocity into components, just like this. Okay? Okay. You guys get that? But let's see what questions are being asked anyway. Okay. Find the initial vertical component velocity. Find the and horizontal component. Okay, actually, so number 11 and number 12 are in fact those two right there. Okay. So I'm trying to help you guys out by asking these in order, right? Okay. Find the two components. How fast across, how fast up initially. Number 13, find the time it took the cannonball to reach the ground. So what's the total hang time? Right. If you look at the full picture, like what's the total hang time? Right. And then the last question, number 14, how far did the cannonball go before striking the ground? Which sure does sound a lot like this poster right here. How far did it go? I bet this could answer the question, this range formula. Maybe I'll come back and use this range formula to check the answer, right? Okay. Now there's a whole process where you can prove this with a process too. I'm gonna walk you guys through the process. Let's go do that. Some paper out here. Okay, I have 70 meters per second at 30 degrees above the horizontal. So here's the ground, here's a cannon. Here's, I'll call it 30 degrees right there above the horizontal about. Okay, V blast equals 70 meters per second. Okay. The number on your paper is probably different. Unless you're lucky, might be the same. Let's call it 30 degrees. My picture's not quite to scale, but you guys get the idea, right? And you guys know this is gonna arc into a parabola shape and land, downrange probably right about there. So something like that. Nice parabola. Okay. Right, so the very first step to all these type problems is, break this blast velocity into components. Say, well, how fast is it actually headed downrange? That's the horizontal component. And how fast was it initially blasted straight upwards, as if you threw a ball straight upwards? It's got that component too. Guess that? Okay. How do you get this V sub x? What's V sub x equal to? What times what? Who remembers trigonometry? Because I just drew a right triangle, right? Right triangle. This is equal to what times what? 70 meters per second. Right. And we're translating from hypotenuse to adjacent to 30 degrees. Guys, if you're translating from hypotenuse to adjacent to 30 degrees, is that sine or cosine? Cosine, yeah. So I'm taking my 70 meter per second total blast speed, multiplying by cosine of 30 degrees. Right. Calculator time. And it comes up to 60.6 meters per second. Now, because that's the horizontal component of the motion for this projectile, is that constant all the way across the field? Is it always going across the field at that rate? Yes, it is, right? Because gravity doesn't pull horizontally, so that's not going to change it. And we've been ignoring air drag, so yeah, it's just constant that rate all the way across the field. Right? Now, we can't figure out how far it goes until we know how much time, and how much time depends on this component, this vertical component, and also the gravity field. So let's get this component right here. Now this one I'm going to call V initial in the y direction. You guys see like a double subscript there, V naught y, right? Because it's vertical, but it's only for like the very first instant, and then it immediately starts slowing down. But I can use the same technique. Right? 70 meters per second times what? Sine of 30 degrees. Okay. Now, if you're so lucky to have a 30-degree angle, does anybody know what sine of 30 degrees is? It's a special fraction. It's 1/2. Let me show you guys. If I flip in a sine where the cosine used to be, 70 cosine of 30 degrees. It's 35 exactly. Right. It's 35 meters per second. 35 meters per second. Okay. Now that's v initial in the y direction. Okay. 1 second later, it's going 25. 1 second later, 15. Right. So it's slowing down by 10 meters per second every passing second. Okay. Wow. Actually, I used 9.8 meters per second squared on this paper. So that's what we're going to do. Okay. So there's number 11 and number 12 right there. Boom, boom. Number 11, number 12. Boom, boom. You guys got number 11, number 12? All right, are we good? All right, number 13, the time it takes the cannonball to get from here to here. Now, there's different techniques you can use to figure out the total hang time. One technique you could use is you could say, well, if I'm going from the ground back to the ground, guys, what is the displacement? What's the vertical displacement from the ground back to the ground? Zero meters. That's one way you can do it. Another way you can do it is you can break this problem in half. You can say, well, I wonder how much time it takes to get to the peak. And then whatever time that is, I can just double that time because it takes the same time to fall back down to the ground. Okay, let me go ahead and do it that way. Is it okay if I break this problem in half? Is that okay? Right, get the time to the peak and then just double that for the total hang time. Right, let's do it that way. Okay. If I choose that method, then right at the very top, right at the very top of the peak, right, how fast is it moving vertically? Is it moving up or down at all right at the very top? No. So its vertical velocity would be equal to 0 meters per second. Right? Okay, so I know the initial velocity in the vertical direction, like, as if you threw a ball straight up. I know at the peak that goes to 0. And I want to figure out something about time. Okay? Which kinematic equation is that going to fall into with this method that I'm going? First, second, or third? I know 2 velocities and I wanted time. It's got to be the second one. Got to be the second one. Okay. I see. There's initial final velocity. Something about time I can solve for. Oh, and I know the gravity field. Yeah, give me this one. Again, this is not the only way to solve this problem. This is one way to do it. So I just picked one and ran with it. So I'll say v final in the y direction equals v initial in the y direction minus g times t. Kind of modified that a little bit. Like I said, it looks like I'm calling maybe up positive and down negative. That's why I'm like subtracting. Because you guys know it's going to be like slowing down on the way up. Now, VF in the y direction. At the peak, this would be 0 meters per second. Okay. Now, once I plug in that number right there, I have to be careful because I know already that means I've broken this problem in half. Because I'm only calculating to that top point right there. Okay. So V initial in the y direction is still my 35 meters per second, which got from trigonometry. I'm subtracting, here on this paper I printed 9.8 meters per second squared for gravity, so let me just go ahead and pop that in there. Okay. And the t, let's see if you guys are following. Guys, does this t represent the total hang time or half the total hang time? What is that t? Based on how I set this up? How many guys think that based on the numbers that I plugged in so far, this t only represents half the total hang time? It's only going to get me to the very top. What do you guys think that? Yeah. And how would you know? Because I plugged in 0 meters per second for my final velocity in the vertical direction. And there's only one place that happens. That's at the very top of this curve. It goes to 0 vertical velocity, right? Still moving horizontally, but this is a vertical equation. This is all vertical analysis I'm doing right here. This is all vertical, isn't it? Right. So I'm going to call this t about half. I'll put the subscript half because I know it's half of the total hang time. Okay. You guys get that? Right. Okay. Are you guys good with that setup? Right. Because if you're good with that setup, then the rest of this is just going to be an algebra process, and the answer is just going to fall out right in front of us. Right? So take the 9.8t, add it over, divide by 9.8. T half the total hang time is 35 meters per second divided by 9.8 meters per second squared, okay, which looks like 3.57 seconds. Okay. Takes about 3.5 seconds to reach the peak, at least with my numbers on my paper. Okay. If that's true, would it take about another 3.5 seconds to fall back down? So what's the total hang time? This would be 2 times that midway time, right? Okay. So times 2. So the total hang time is 7.14 seconds. Okay. Is that the answer to? Yeah, that's the answer to number 13. That's the answer to number 13. Okay, you guys got that? Right, all good so far? Okay. Let me do a little bit of overkill because I think we got enough spare time in class I can do this. Let me show you another way you also could have solved that. You guys want to see another way you could have solved that? So let me backtrack a little bit. Suppose I wanted to use a different method. What if I use that method where I go from the ground back to the ground and I just go ahead and get the full hang time in one shot? Okay. I can use the first kinematic equation. I could say y equals v naught y total hang time minus 1/2 g total hang time squared. I could do that. Okay. Hey guys, if you go from the ground back to the ground, what's the vertical displacement again? That'd be 0 meters right there. Okay. I could factor a t out of here. So v naught y minus 1/2 gt, and then factor a t out. Okay. Now if I divide both sides by t, 0 divided by t, this goes away. Knocks that out, right? Okay. Remember, the way I'm setting this up, this will solve for the total hang time, okay, which you guys already know, but I'm just showing you a different way to also get there. Okay. Now I can start popping numbers in. 0 equals, I got my 35 meters per second straight upwards here, minus 1/2 times 9.8 meters per second squared times t hang, the total hang time. Okay, guys see that? Okay. Do a little algebra shuffle. I guess I'm gonna add this over, divide by 1/2 of 9.8. So it's 35 meters per second divided by 4.9 meters per second squared is one way to think of it. Okay. Again, I know what the answer has to be. It better be 7.14 seconds, because that's what I got before. You guys think it's going to be 7.14 seconds? I hope so. 35 divided by 4.9. Oh, it's 7.14 seconds. There you go. It's same thing we got before. Okay. Okay. So here, there's 2 different ways to get number 13. You guys see 2 different ways? Okay. So the first way I showed you guys is I broke this problem in half. Said, well, goes to 0 vertical velocity at the top. So I could use the second kinematic equation, get half the hang time, and then just double it. The other way I could do it is I could break out the first kinematic equation, say there's 0 displacement from the plane back to the plane, and then just get the full hang time. But either way, I get the same hang time. Is that? Okay. And finally, number 14. How far does the cannonball go before striking the ground? That's to say, what's the horizontal displacement? Guys, horizontal. Oh, well, we know some stuff about horizontal. We know how fast it's going across. It's going this fast across, this many meters per second. And we also know how much time it does that for. Is it accelerating horizontally? No. So all you need is x equals v sub x times t. That'll take care of that. Okay. So how far does it go horizontally? Well, I know how fast it's going horizontally. That's this number, meters per second. We got that from trigonometry. That was the first thing we did, a little bit of trigonometry. Okay. And I know the hang time. I showed you guys 2 different ways to get the hang time. So either way, it's the same number. Pop, pop. So this many meters per second across for this many seconds. I'm getting this many meters. There you go. That's the horizontal displacement in meters. Yeah. The final vertical velocity? Right. Wait. Are you talking about for this exact same scenario? Okay. In general, one way to get it is however much time has passed, you can use this one. You can say, here's final vertical velocity. You know, it's accelerating down at 9.8 meters per second squared. You say that how much time it happened for. Oh, okay. Do you know how far it fell? Like a height change? Because in that case, you could use the third one. You say final vertical velocity, right? Initial vertical velocity, right? And then accelerating down for some height change. There could be a height change in that case. Do that, right? So if you know the time of fall, you use the second equation. If you know the height of fall, you can use the third one. Okay. Okay. Let me go ahead and there's one more thing I want to show you guys on this one before I wrap it up. Okay. Number 14. You could sort of, as an alternative, use the range formula because this is sort of like a pre-solved general solution. Let me show you guys that this will also get you the exact same answer. The blast speed of my cannon was 70 meters per second. I can pop that in right there. Let's go 70 meters per second, square that. Okay. 70 meters per second, square that. Divide by 9.8 meters per second squared. That's right there. Multiply by sine of the double angle. Now my angle was 30 degrees, so I'll do 2 times 30 degrees. Okay. Now I know what the answer better be. The only answer on the screen better be 433 meters, right? 433 meters. Let's see if it takes care of it. Oh, it's 433 meters. Look over there, it says 433 meters. All right, you guys see that? All right, so go ahead, turn your labs into the gray tray, and I will walk around and answer any last questions you guys have.